Okay, good afternoon, everyone. Welcome to our industry seminar speaker series. Today we are hosting Dr. Tiffany Santos from Western Digital. She is double MIT graduate, and her PhD was very closely related to the topic of memory, so spin polarized tunneling magnetic tunnel junctions. She is currently director of non-volatile memory materials research division at Western Digital in San Jose, California, where she is now, as I presume. Okay, where she leads a team of working on materials for magnetic random access memory technology and all other related project. Okay, joined the company in 2011. And before that, she was distinguished postdoctoral fellow and later assistant scientist at Center for Nanoscale Materials, Oregon National Laboratory. Okay, it's a long bio for a lot of successful achievements. I would probably not go through all of it for the sake of time. And I will just let you start, Tiffany.
Okay, thank you, Oleg, for that introduction. And thank you for this invitation to come and share what we're doing in Western Digital Research. Okay. The title of my talk is Spins, Bits, and Flips, Essentials for High Density MRAM, Magnetic Random Access Memory. And I am a distinguished lecturer of the IEEE Magnetic Society. So this is my distinguished lecture talk. So I'll just say a few words about the society. It is the leading organization for bringing together people that do research in magnetism. There are active chapters in various points around the globe, and we organize major conferences focused on magnetism and its applications. Those would be Intermag and the MMM conference, but we also organize smaller workshops as well. And we give financial assistance to students traveling to attend these events. So if you're not already a member, I encourage you to go to the website of the IEEE Magnetic Society and have a look at what the society has to offer and consider joining to be part of this great community. So I am at Western Digital. The headquarters is located in San Jose, California, and that's where I'm sitting in the offices today. Our two main products in mass production are the hard disk drive, which is a magnetic data storage device, and a solid state drive, which is based on NAND flash. But I'm really not going to be focusing on those today. What I would like to share with you is the exciting research that we're doing in the research division of Western Digital on magnetic random access memory, a non-volatile memory. So in this talk, I'll start out by giving a history of magnetic tunnel junctions because they're the key element in the applications that I will be discussing today. It is the key element in MRAM, magnetic random access memory, and also the hard disk drive that I'll touch on a bit. Then I'll go into an introduction on spin transfer torque, MRAM. Then I will describe the challenges that we're facing and trying to overcome to push towards a high density spin transfer torque MRAM. I'll give a couple examples of experimental works that we have been doing in our research lab to address these challenges. One is materials engineering of the free layer of the MRAM material stack, and the other is a nano-fabrication experiment patterning MRAM bits at tight pitch, and then I will conclude. So a great place to start describing the history of the magnetic tunnel junction is with Ivar Gavar. He was trained as a mechanical engineer and he was working at General Electric in New York in the late 1950s. And he wanted to study conductance between metals. So his idea for his experiment was to start with an aluminum electrode and then use its natural oxide at the surface, aluminum oxide, as a tunnel barrier, and he put a superconducting lead counter electrode to make this tri-layer tunnel junction. And With this tunnel junction, he showed the energy gap in the superconductor measured by electron tunneling from the aluminum metal. So this was a remarkable verification of the BCS theory, and for this he was awarded the Nobel Prize in Physics in 1973. A little while later, at the Francis Bitter Magnet Lab at MIT, Paul Tedrow and Robert Meservey, they were also using aluminum electrodes and aluminum oxide tunnel barriers, but this time the aluminum was the superconductor. They used a ferromagnetic nickel as the counter electrode in this tunnel junction structure. And with this tunnel junction, they showed the asymmetry of the spin density of states in the ferromagnetic nickel, measured using the aluminum superconductor as a spin detector. And this was the first experiment showing that spin is conserved in the tunneling process. And this is something that we take for granted in technologies using magnetic tunnel junctions today. But this is the first experiment showing this phenomena, and it opened up the door to this rich field of physics called spin polarized tunneling. Let's see, let me adjust these controls for a moment. Okay. Then a few years later, there's a graduate student working towards his PhD in France, Michel Gillier, and he was inspired by the work of Meservey and Tedrow. He had learned that spin was conserved in the tunneling process, and he introduced a model for tunneling between two ferromagnets in a magnetic tunnel junction. So he proposed to use two ferromagnetic electrodes, shown here, iron and cobalt, and an insulating tunnel barrier in between. A tunnel barrier is typically 1 to 2 nanometers thick. And he proposed that with such a magnetic tunnel junction, because spin is conserved in the tunneling process, you should see two well-defined resistance states. So what's special about ferromagnet is that it has this um, asymmetry of the density of states. So shown here, there are a lot more spin up electrons than spin down. So that when the two ferromagnets have their magnetization oriented parallel to each other, there are a lot of spin up electrons at the Fermi level tunneling into a lot of spin up empty states in the other ferromagnet. And this results in a high tunnel current and correspondingly a low resistance state. When the two ferromagnets have their magnetization oriented anti-parallel to each other, there's a mismatch of this spin density of states. And this results in a low tunnel current and correspondingly a high resistance state. So Julier defined a tunnel magnetoresistance ratio as the difference between the high and low resistance states, or the anti-parallel and parallel resistance states, over the resistance of the parallel state. And for his PhD thesis work, he used an amorphous germanium tunnel barrier, and he saw at low temperature a TMR ratio of 14%. However, going to room temperature, there was no more TMR. And there was no room temperature TMR until 20 years later, um, until this team here at the Francis Bitter Magnet Lab at MIT published this physical review letters showing TMR at room temperature for the first time. And this team was made up of a principal investigator, Jagadish Mudera. And then also on this team was Lisa Kender. She was a high school student at the time. And this was a very ambitious 8 weeks summer project assigned to her. Also, there was Terilyn Wong, a freshman undergraduate student, and Robert Meservey, who's retired at the time. So it's a fun example of a team of all different points in their career coming together to make this important discovery. Also published in 1995, Professor Miyazaki and Tezuka, they also observed in TMR at room temperature as well. And this is with aluminum oxide tunnel barriers in between the two ferromagnetic electrodes. It was this discovery alone that led to the major applications for magnetic tunnel junctions. And I will get to those in a moment. But before that, I want to cover a couple more important milestones for magnetic tunnel junctions along the way. In 2001, there was a first principles calculation saying that if you use crystalline magnesium oxide tunnel barriers and you put iron electrodes top and bottom here, and you have coherent epitaxy across the interfaces here, you'll have a special situation where you have fully spin polarized electrons in the iron. And then in the MgO, it will have a lower tunnel barrier height, or making it easier to tunnel for these fully spin polarized electrons. So it's a specific combination with this specific structure across the interfaces. But if you have this tunnel junction structure, then you could get very high TMR values approaching 1000%. So this was very motivating for experimentalists to pursue. And indeed, just a few years later, published in 2004 by a couple teams in Nature Materials, their very high TMR values at room temperature using MgO tunnel barriers. So this is 180% by Shinji Yuasa and colleagues, and 220% by Stuart Parkin and colleagues. So over time, as the quality of making the MgO tunnel barriers and iron-based electrodes, as that progressed, the TMR values got higher and higher until today you can see upwards of 600% at room temperature for MgO tunnel barriers. And this is compared to what you can see with amorphous aluminum oxide tunnel barriers. The best values are around 80%. And that brings us to the early products using magnetic tunnel junctions, and they were used as the read head in the hard disk drives. And this was first introduced by Seagate in 2004. So the first magnetic tunnel junctions as read heads had titanium oxide tunnel barriers. The other application, not as prominent as the hard disk drive, but we have toggle magnetic random access memory, first introduced by Freescale, now known as Everspin, in 2006. And toggle MRAM is still in production today by Everspin, and it uses aluminum oxide tunnel barriers. So I'll describe a bit more about these applications. For the hard disk drive, we are all using magnetic tunnel junctions on a daily basis. And a great example of that is that this talk is getting recorded right now. It's getting streamed by Zoom to a data center somewhere where it's getting stored onto a hard drive. And then sometime later, if somebody ever wants to see this video, it will be a magnetic tunnel junction that will read the data from that hard drive and play its role to bring it to you, the viewer. So it's hard disk drive storage technology that's behind the cloud storage, and you're using it on a daily basis. If you watch YouTube videos, Netflix videos, or you store your data on a major database like Box or Dropbox. And this is the way that the data is recalled from the disk of a hard disk drive. So here's the inside of the hard disk drive. The major components are this media disk, which has magnetic material coated on both surfaces, top and bottom. And if you take a powerful microscope, like a TEM microscope, transmission electron microscope, and you look at this shiny film surface, you'll actually see that it's a network of magnetic nanoparticles, and groups of them are magnetized together to form a bit. of data, so the zeros and ones, and that's shown schematically here in the red and the purple colors, showing the zeros and ones of written on a track on the media surface. The other major component here is this arm, and the head is located at the tip of this arm and it has a motor. It can sweep back and forth, and as the disc is spinning rapidly, and it can access any point on the surface of the disc top, and there's another one at the bottom for every disc. And the major components of the head are the writer portion, which writes the bits into the media on the disc, and the reading head, which has the magnetic tunnel junction sensor. So these bits in the magnetic media layer, they have stray fields coming into and out of the bits depending on their magnetic orientation. This is perpendicular magnetization, so up or down. And that's also shown schematically here in the orange and black in the plane of the slide. So the magnetic tunnel junction in the read head has to get very, very close to the surface of the media in order to sense these stray fields. And you have the magnetic tunnel junction here. The barrier is this white layer. And you have the magnetic reference layer underneath and the magnetic free layer on top, and a current passing perpendicularly through the layers. And so the free layer is free to cant its magnetization as influenced by the stray fields and depending on the up or down orientation of the bits. So as a result, you'll get a higher resistance state for bits with magnetization going into the plane of the slide, and lower resistance for bits having a stray field coming up out of the plane of the slide. So this is a transfer curve showing resistance versus the field strength. And this is how the data is read from the hard drive using a magnetic tunnel junction. The other application is in MRAM as a memory, random access memory. And in a toggle MRAM product, it's a magnetic tunnel junction in this grid here at every intersection of a word line and bit line. And you pass, the way it operates is that you pass a high current to generate a local magnetic field that can flip the magnetization of the free layer to be parallel or anti-parallel relative to the fixed layer. So this is how you store the zeros and ones in this random access memory scheme. So now I'll introduce spin transfer torque MRAM. So as I described for toggle, you use a magnetic field generated by current pulses in the word lines and bit lines. So this type of writing scheme, it does not scale well to small dimensions. But for spin transfer torque MRAM, you use the current coming from a transistor to flip the magnetization of the free layer in the magnetic tunnel junction. In this type of writing scheme, it does scale well to small dimensions. You can see that easily in this schematic here on the right side. It's a top-down SEM image where on the right we have 16 perpendicular magnetic tunnel junction bits. They're about 60 nanometers in diameter, and they fit into the area occupied by just one toggle MRAM bit. So it's clear that moving forward, it will be spin transfer torque MRAM that we can use to achieve a higher density rather than a toggle MRAM. And indeed, there are STT-MRAM products available now. They are embedded MRAM products. They are targeted to be a replacement for embedded flash because they scale better to the 22 nanometer semiconductor technology node and beyond that, better than what embedded flash can do. So we have these major companies here partnering with these major foundries to produce embedded MRAM products that are targeted to be embedded flash replacement or slow SRAM. And that's happened just in the past 5 years. So I'll describe what is a spin transfer torque MRAM cell. It's one transistor to one magnetic tunnel junction, and the transistor supplies the right current to switch the free layer magnetization to be parallel or anti-parallel to the reference layer to store your bits zeros and ones. So it uses the current from the transistor to do this, and there's no magnetic field required. So it's a magnetic device that does not need a magnetic field. So the writing happens by spin transfer torque. So you have here in this schematic the three major layers of your magnetic tunnel junction, your reference layer and free layer with the tunnel barrier spacer in between, and you pass a current perpendicularly through the layers. And initially, there's a random spin orientation for the electrons in the current, but then once they pass through the reference layer, then you get a spin polarized current. By conservation of angular momentum, the free layer feels a torque acting upon it by the polarized spins coming from the reference layer. And if the incoming current is high enough, then the torque will be large enough to switch the magnetization. So spin transfer torque was discovered by two theorists in 1996, John Slonczewski and Luc Bourget. And here I'm showing the magnetization dynamics described by the Landau-Lifshitz-Gilbert equation here, showing the precessional motion of the magnetization around the effective applied field. And when you pass a current, then you add the Slonczewski terms. So I want to point out here, this green term here, the spin transfer torque one, that flips the magnetization. You can see that it is directly opposed by the damping torque, the red one, that wants to pull the moment back toward the applied field. For this reason, when we're engineering the free layer, we want it to have a very small damping constant so that we can have the most effective or efficient spin transfer torque to flip the magnetization. So here's sort of an example of the reading and writing of the magnetic tunnel junction for the STT-MRAM cell. And I'm showing here resistance versus voltage. So if we start here at the high resistance state, for example, written bit of 1, where the two ferromagnets have their magnetization oriented anti-parallel to each other. So we're at the high resistance state, and you can read this with a low bias. But then when we want to write and flip from anti-parallel to parallel state, you apply a voltage surpassing the critical voltage for flipping till we get to the low resistance state, or for example, a written bit of 0, where the two ferromagnets are parallel. Then if you want to flip back to the anti-parallel state, you apply a bias of opposite polarity to get back to the anti-parallel or high resistance state. So if you take the same tunnel junction and flip it by magnetic field, we would see this resistance versus field transfer curve here. And the reversal of the free layer can happen in a couple different ways. It largely depends on the size of the bit and the magnetic properties of the free layer. So for small bit sizes, for example, 25 nanometers or less, the flipping of the free layer happens by coherent rotation. So this is shown schematically here on the right side. This is a micromagnetic simulation showing these reversal mechanisms. So for example, here you start out with red, all of the spins are pointed up in this perpendicular junction. And then To flip, they rotate together as a single domain till they're all pointed down, indicated by the blue color. For bit sizes that are larger, 25 nanometers or above, the reversal happens by domain wall nucleation and propagation. And that is shown in this simulation here. This blue domain is nucleating in the center and then propagates outward until you get complete flipping of the free layer, the blue here. And you can see that this x-axis here is time, that's a longer process. And it's made longer if you have a free layer with a smaller exchange stiffness A compared to a higher exchange stiffness for the panel at the top. It takes shorter time to flip. However, regardless, the domain wall motion for the reversal, it'll take longer than flipping by coherent rotation. So we see here that if we want fast switching, we need to be in the regime where we have small device sizes where they flip by coherent rotation. So my role here in the MRAM research team at Western Digital is to do the film deposition of the MRAM stack and tailor its magnetic properties. So I'll share with you a couple tricks that we use day in and day out to make these magnetic tunnel junctions in the MRAM stack. So one trick addresses the question, how do you get epitaxial cobalt iron MgO interfaces that are needed for high TMR, as I described previously? How do you get these epitaxial interfaces in a manufacturable process? So this trick was published in Applied Physics Letters in 2005. And what we do, this is used in the production of reed heads as well. We start with an amorphous cobalt iron boron electrode. Then so we make the cobalt iron amorphous by alloying in 20 to 30% boron. Then we do sputter deposition of the MgO tunnel barrier, and on an amorphous surface, it's very convenient for us that we get the desired texture, 001 orientation of the MgO, which has a rock salt cubic crystal lattice. Then we put amorphous cobalt iron boron electrode at the top. It's a typical flow that the MRAM stack undergoes a post-anneal step after deposition. And during the post-anneal, the boron atoms diffuse away, allowing the cobalt and iron atoms to arrange themselves on the lattice template established by the MgO tunnel barrier. This is called solid phase epitaxy, and this is how you get the high quality MgO cobalt iron interfaces that are needed for high TMR. You end up with a textured film structure. The other trick I want to describe addresses the question, how do you get cobalt iron with perpendicular magnetization? Because cobalt iron, really in the bulk form, it really wants to be in plane. And indeed, it's in plane magnetization for tunnel junctions used for reed heads. But in MRAM, we are using a very similar material set, but we want the cobalt iron boron to be perpendicular, because this will lead to a lower switching current and a higher density of MRAM. So the way that we get perpendicular magnetization is just to make the cobalt iron boron layers very, very thin. You can see here, once you make it thin, the interfaces start to dominate and overcome the bulk. And then you get a perpendicular magnetic anisotropy generated at the interfaces, which is understood to be due to orbital hybridization between the iron and the oxygen. So this was shown in a theoretical study. And the trick of using thin cobalt iron boron itself was independently discovered by a couple groups, and and published in 2010, 2011. So you can see here, this is anisotropy versus cobalt iron boron film thickness. And as you thin down, you get a crossover at about 1.5 nanometers between in plane and perpendicular magnetization. And then conventional STT-MRAM stacks now, it's typical that we use an MgO cap layer as well as the MgO barrier, so that there's MgO at both interfaces of the free layer to further enhance this interfacially generated anisotropy. So I'll review some main performance characteristics for STT-MRAM. One is the writing. So as I described, this is happens by spin transfer torque, and it's characterized by a critical switching current density JC0. You can see here that the critical switching current density is largely dependent upon many materials parameters of the free layer: the saturation magnetization, the anisotropy field, the damping parameter, and the thickness. Reading happens by TMR, which is also largely dependent upon materials. As I said, it's a specific iron-based electrode with MgO tunnel barrier that gives rise to high TMR with good quality of good crystalline quality of the junction. Retention, this is due to the perpendicular magnetic anisotropy of the free layer. And retention is how long can the free layer retain its magnetization in the written state, up or down, before you get a thermally activated reversal. So this is characterized by a thermal stability factor delta, and is typically reported as units of time. For example, a number of hours or a number of years until you get a thermally activated flipping of the free layer and your data is lost. Endurance is the number of write cycles reached before a specified failure rate. For example, a failure rate of 10 parts per million. So how many times can you pass a high current through the MgO tunnel barrier before you get a failure? And the typical failure is a breakdown of the MgO tunnel barrier to short. And different MRAM products you can tailor the properties of the MRAM stack toward target values for different MRAM products. For example, for embedded flash, which is a product now, they typically use magnetic tunnel junction bit sizes 40 nanometers and above, and the retention is targeted to be 10 years at an elevated operating temperature. Write current above 100 microamps, TMR over 100%, and endurance about 1 million cycles. However, if you want to have a higher performance product, for example, a standalone chip that could function as a DRAM replacement, then you're going to need magnetic tunnel junction sizes that are 20 nanometers or less. Write current very small, less than 20 microamps, TMR approaching 300%, and endurance 10 to the 12 cycles. And the reason why you would want a high performance MRAM is because we are now living in an era of big data applications which have massive storage and performance requirements. For example, our devices are now connected in the Internet of Things, and we have applications of big data analytics in several sectors of our economy, for example, in retail, healthcare, and finance. And then a popular application here in the Bay Area is self-driving cars, which require real-time processing of visual data. So these applications, they require an effective memory hierarchy that is fast and low power, and they're driving a need to bring a high performance memory closer to the computing units. So this motivates our research into new physical mechanisms like spin transfer torque for storing information better than the memories that are available to us today. So this brings me to the challenges as we try to progress to a high density spin transfer torque MRAM, and then a couple examples of research projects that we've been doing at Western Digital. So to achieve a high density STT-MRAM, we need to target bit sizes that are 20 nanometers or smaller. And there are a number of challenges to get there. Materials wise, as soon as you reduce the volume of the free layer, which you're going to do to get to small bits, you're going to have the volume V here, you're going to have a problem with low thermal stability. So you compensate for that by increasing the perpendicular magnetic anisotropy, but you need to do that while still keeping the switching current density low, because very high currents will cause breakdown of your MgO tunnel barrier and you'll have endurance issues. And also, a high density MRAM requires a high density of very small transistors, but small transistors can only supply small current. And you still need to have enough current to switch the MRAM free layer. So this is a difficult trade-off for anybody working in MRAM. Another challenge is fabrication related, how to etch a high density of MRAM bits at tight pitch, and to do that while maintaining tight distributions of your various performance parameters. Now, because higher distributions are expected for small cell sizes, then this will require a TMR values approaching 300% in order to reduce read errors. So that is also a challenge as well. So the first one I'll talk about is addressing this this trade-off here between thermal stability and low switching current. You can see that if we increase perpendicular magnetic anisotropy by increasing saturation, magnetization, and anisotropy field, that will directly cause the increase of the switching current density. So for this reason, the damping parameter becomes key with trying to engineer that to be as low as possible. So our approach to doing this is materials engineering of the free layer to try to achieve a low switching current. And we have modified it to be very thin. So a conventional free layer has a thickness 20 to 24 angstroms typically. And it is made up of a cobalt iron boron on top of an MgO barrier with an MgO cap, and inserted somewhere within the cobalt iron boron is a heavy metal spacer. And for us in this experiment, it's tungsten. So the purpose of the tungsten is to give the boron atoms a place to go during the post-anneal step. You want them to diffuse away from this critical cobalt iron MgO interface so that you can have the solid phase epitaxy, and you don't want the boron atoms going towards your barrier to reduce your barrier quality and have poor TMR. So we put in this heavy metal here, and the boron atoms will diffuse to that layer. Other than that function, the tungsten will reduce the saturation magnetization and increase the damping parameter. So for that reason, we want to minimize how much tungsten is really necessary to maintain perpendicular magnetic anisotropy. So we found that we're able to reduce the tungsten amount by just overall reducing the free layer thickness. And here, for example, down to 12 angstroms. We found that we were able to improve the magnetic properties even further by taking this single tungsten spacer and keeping the total thickness constant, but splitting it into two thinner layers, but still total free layer thickness is 12 angstroms. So here's a cross-section TEM as an example showing a 13 angstrom free layer in between MgO barrier and MgO cap. So we proceeded to use this free layer design for a ladder of free layer thicknesses, 17 angstroms, 13 angstroms, and down to 12 angstroms. And by going smaller in thickness, we're able to reduce the amount of tungsten that is needed to keep the free layer perpendicular. By reducing the tungsten amount, we see that we can significantly increase the saturation magnetization and keep the damping parameter low. So we started out with a low damping parameter, and by reducing tungsten, we're able to get it even lower. And then for the exchange stiffness, we find that it's really approaching what we know for bulk iron. So the quality of these free layers and the magnetic properties are very good, even though they've become quite thin. So we proceeded to make bottom-pinned STT-MRAM devices with diameters in a range of 55 to 130 nanometers using an optical lithography process. And with these devices, we see TMR values in the range of 100 to 125%. And the coercivity, or the coercive field for field switching, is in a healthy range, 2.2 to 2.6 kilo oersteds for the smallest devices. So in this experiment, the two main things we wanted to know is the thermal stability factor and the switching current density. So for the thermal stability factor, this is determined from field switching probability measurements, where we have those results and we fit them to a domain wall reversal model, since we are in a device size regime where we do expect domain wall reversal. So from this analysis, we get domain wall width, domain wall energy density, and the thermal stability factor delta, which is found from domain wall energy density multiplied by diameter and film thickness over KBT. And we see here that it's the thinner free layers with the better magnetic properties that have the higher domain wall energy density, and so that they're able to maintain a high thermal stability factor even though they're very thin. For critical switching current density JC0, this is determined by fitting pulse width dependence of the critical voltage using a thermal activation model for spin transfer torque switching. So we find here that the critical switching current density is significantly lower for the thinner free layers, like by 30% compared to the 17 angstrom thickest free layer of our ladder here. And then for spin transfer torque efficiency, this is a common figure of merit used for studying MRAM, is defined as the thermal stability factor delta over critical current. We see that the thin free layers, they have the highest efficiency because they have the lowest switching current density, yet maintaining high thermal stability. The other study that I want to describe addresses this fabrication challenge of etching MRAM bits at tight pitch. And at Western Digital, we had a goal of making a 50 nanometer full pitch array, being able to confirm physical separation of the bits and do an electrical testing to see the free layer switching. And 50 nanometer full pitch means it's 50 nanometer distance between the center of one MRAM pillar to the center of a neighboring pillar. So looking in literature, there are some really nice demonstrations experimentally of high quality, high performing, very small MRAM bits. Here's just some examples here. IBM, Samsung showed an 11 nanometer bit. Here are a couple 20 nanometer bits, but we call them isolated bits. You can see you have the MRAM pillar with no neighbors close by. making MRAM bits in an array at tight pitch is quite challenging because you need to remove a lot of metal. The MRAM stack is mostly made up of metal. So you have to etch it away. And what's going to happen is that you'll get redeposition of this etched metal onto the sidewalls of the pillars. And that will typically lead to a short across your very thin MgO tunnel barrier. So you can make the array, but then easily find that all the bits are shorted and you get no electrical data. So that's what has happened here in this Samsung demo a while back. You have a tight pitch array of MRAM bits, but no electrical data. So the best demo that we know of to date was back in 2016 by SK Hynix and Toshiba. It's a 4 gigabit demo with electrical data. And so this MRAM array is with 90 nanometer full pitch. But to be competitive with a DRAM density, you need to show at least a 56 nanometer full pitch. So this is our approach here to get a tight pitch MRAM array. So we start out with blanket film of the magnetic tunnel junction stack and put the hard mask on top. The hard mask is used to define the MRAM pillars through the etch step. So first we make the hard mask by patterning it with e-beam lithography, and then the hard mask, it's made up of tantalum nitride, diamond-like carbon, and chrome. You define the hard mask by doing reactive ion etching. And so here's the patterned hard mask here in this tilted SEM image. Here's a, tilted view and then a top-down view of the hard mask. So the main requirements for the hard mask that you have very straight slide walls and a high aspect ratio. With this hard mask, then we proceed to etch into the MRAM stack. This is done by ion milling, first at a low angle to get into the depth of the MRAM stack, and then a second etch step at a high angle, and the substrate is rotating during this etch process where you mill away the redeposited material on the sidewalls to prevent this shunting across the barrier. And here is the tilted SEM image of the MRAM bit array. So now we can make the MRAM array, but now we want to have electrical contacts and to be able to see this, confirm the switching. And we don't have easy access to expensive CMOS. So we do the best we can in our research lab to make contacts, and we came up with this bottom point contact scheme where we make metallic contact pillars here defined by e-beam lithography, and then a second e-beam step to make the arms that go from the pillar out to the contact pads. Then we put a fill with a dielectric and chemical mechanical polishing to make the surface very, very smooth for the MRAM stack deposition. And then the hard mask on top, we define, we fabricate the MRAM array using the process I described previously. You can see the alignment of individual pillars to the bottom point contacts is critical here. We use spin-on glass for planarization, and then we put a common top electrode at the top, and you can see schematically in cross-section what we're hoping to get here, and I can show you in the TEM images as well. So I'll describe here starting on the left side. These are SEM images of the individual bottom point contacts, first the contacts and then the arms, and then we put the MRAM array on top of that after the planarization. If we take a diagonal slice through this MRAM array on the bottom point contacts, then we get these cross-section TEM images. Here, the top one is for a 52 nanometer tight pitch, and the bottom one is for a 50 nanometer pitch. And you can see excellent alignment between the bottom point contact and the MRAM pillar. You can see physical separation of the bits, and we know that we have adequate removal of the sidewall deposition because we're able to make electrical measurements showing good magnetic properties because the TMR is at 100% for these very small bits. So this brings me to my conclusion. What I wanted to show in this lecture today is that we are all using magnetic tunnel junctions on a daily basis to store our data, and this has been the result of major breakthroughs, major discoveries at the basic research level over decades. For example, the first observation of spin polarized tunneling, and then 20 years later, over 20 years later, finally room temperature TMR for the first time, and so forth. So we continue to make advancements such as being able to switch with spin transfer torque, and you don't need a local magnetic field. So this has given rise to spin transfer torque MRAM as a non-volatile memory technology, and there are embedded MRAM products available now. So further innovation in materials and fabrication and memory architecture are needed to push spin transfer torque MRAM to even higher density with cell sizes 20 nanometers and below. So I want to thank the IEEE Magnetic Society and then also these folks here that inspired me to put this lecture together. Thank you very much for your attention.
Thank you, Dr. Santos, for such a detailed introduction. It's kind of a bring us up to speed because some of us were falling behind the developments, including me. It's been a while for me personally. So we have a few questions from the audience. Specifically, well, thanks, Rabiul, for a list of questions, not just one. Okay, I will just read them one after another. And number one, could you please explain a little bit more the difference between capping and barrier layer?
Sure. The barrier layer is the most electrically functional part of your magnetic tunnel junction. You have your two magnetic electrodes on the top and bottom. And it's this barrier where you will get your high TMR. The cap, typically the amount of resistance the cap gives to your overall stack is very, very low. In fact, if it has pinholes in it, that's fine. And the function of the cap is really to help give additional perpendicular magnetic anisotropy because it's generated at interfaces. Really, you want it to add very little resistance to your MRAM.
Okay, thank you. Okay, I see questions arriving. I continue with the original list. The first one, again from Rabiul, the same student. Could you please explain the reasons of increase in saturation magnetization when you use tungsten? And I think you were talking about tungsten diffusion.
So, so addition of tungsten will reduce your saturation magnetization. And just as a note, the way we calculate that, we do add in the additional thickness. To get saturation magnetization, you have to divide by the thickness of your material. And we do include the tungsten thickness in that calculation. So adding the tungsten atoms there, they are non-magnetic, and so it is typical and expected that it will reduce the saturation magnetization, and it's also expected that it will reduce the Curie temperature for your material as well.
Okay, I will probably start skipping a little bit because plenty of questions here. One more from Rabiul.
Good. I'm glad to hear of the interest. Yes.
You're learning. Why 3 layers of hard mask are needed?
Yeah.
Specific.
Yes. So the hard mask is tantalum nitride, diamond-like carbon, and chrome. And we define it using a reactive ion etching process. Okay, the hard mask will be largely consumed by the milling as it's trying to protect the MRAM pillar. Now, for this reason, you can expect that the only thing you're going to have left after using it to mill your MRAM bits is tantalum nitride. And tantalum nitride is a conductor. So we choose that so that it can act as a top contact when the process is done. Diamond-like carbon um, is the bulk of the hard mask. It's very resistive to the ion milling. So that is why we use that material. The chrome, very thin chrome at the top, that is there for the purpose of the reactive ion etching step to define the hard mask itself. You have very good etch selectivity between chrome and diamond-like carbon. And so the chrome will protect the diamond-like carbon as you define the hard mask during the reactive ion etching step. So really, maybe it's not so typical that you get so much information from a publication, from an industry, but all of this information is in the paper that I have put the reference for the nano-fabrication demo.
Okay, then I will now move to another person in the audience. From Yushi, how textured magnesium oxide is achieved between two amorphous layers?
Yes.
You
Okay.
did allude it, but very briefly.
Yeah. So MgO itself, it makes a very simple, you just need a rock salt crystal structure. And it is, fortunately for us, it is energetically favorable that the MgO will deposit with the desired texture on an amorphous surface. So we're using that to our advantage, that the MgO is really creating the template that we'll use to define the good quality interface between the MgO and cobalt iron boron, where the cobalt and iron, once the boron diffuses out during the post-anneal step, the cobalt and iron will continue the template established by the MgO for the solid phase epitaxy step.
It's a cool physics behind, I guess. The last question is, in order to get PMA on cobalt ferrum boron, you need really thin films. My question is how to fix the magnetization of the reference layer in such thin film.
Yes, the reference layer is also thin as well. So I think I spent a lot of attention to the free layer because there's a lot of engineering that you do for performance of the spin transfer torque. But the reference layer is also important. You need it to have, it's also very thin. It needs to have good magnetic properties to contribute to the TMR. And it also needs to be very, very stable in its pinning by the hard layer beneath, because the reference layer also feels spin transfer torque, but you don't want it to flip. You need it to be very stable. And so those are kind of the main considerations when we're trying to make a good quality reference layer.
Ethan, I found 2 more questions. Very, very interesting topic. So a lot of thanks to you for their very informative, very detailed presentation. The question is, what would be the most important urgent theoretical problem to further advance STT-MRAM technology? What specific problems you would suggest to investigate for theorists?
How to enhance perpendicular magnetic anisotropy, and preferably without it resulting in higher switching current as well. But then we do have a couple colleagues in our group. They are computational material scientists. And what we're interested in is how to engineer stronger perpendicular magnetic anisotropy for these very thin layers. Is there any specific atoms or layer that you can insert at the interfaces, top, bottom, middle, to help us enhance the PMA? Now, inserting a layer at that cobalt iron MgO interface that's needed for high TMR, you can get some interesting effects that help PMA there, but it will kill your TMR. And so then, like, can you insert something there that will not destroy your TMR? We used tungsten as an example here, but really there are some detrimental aspects to it that, as you see, we're trying to get around it. But we're open to other things that could help us enhance PMA further free layer.
And the next question is, how thin were the amorphous cobalt iron boron layers and the crystalline magnesium oxide layer again? What deposition technique have you used to make these ultra thin layers?
Okay, these are all made by sputtering. The MgO layer, we use RF sputter guns for that. And the whole technique is sputtering. We use industry or production ready tools to make these high quality films.
I guess same applies for research, same applies for scaling up the R&D.
So we, all of our tools and the nano-fabrication demo, this was all made in a research lab. It's not, we are separate from development and manufacturing. We get to have our own dedicated tools to these projects. But just in a research lab, we don't have the capability to really to scale beyond what I'm showing in the demos here. However, we are interested in eventually making a product. So we do think about, okay, beyond our research lab, how can we really scale this and take it to product level?
Okay, thank you. This is all the questions we had from audience. A very last question from me, more or less related to the business of Western Digital. You did show a slide where the players, I guess, developers of technology partner with foundries. I saw there IBM sitting alone, and secondly, I didn't see Western Digital on that slide. So I wonder if you can comment where your company is playing in that field. What's the goals?
Okay.
For your research?
So IBM partners with Samsung.
Okay.
And for Western Digital, you're right. We're not on there. We do not have an MRAM product. MRAM is currently exists in research. However, with some of these demos that I showed today, we do think we have a promising product, and we are now transitioning into development phase and working to figure out how to now scale to make a product.
The journey ahead, I guess.
Yeah.
To get there.
But it's very exciting, actually.
I can imagine.
Yeah, let me say, actually, there's a lot of hiring for fabrication roles, design roles, device testing roles in our new effort.
That maybe some of our students could make it there as well. Okay, then with this, I would like to conclude our seminar today. Thank you, Dr. Santos, again for agreeing to share with us your amazing results. We look forward to see the products on the market and buy them from them as soon as we can. We will We usually clap at the end, but it's not going to happen in virtual environment today. Okay, then.
Thank you.
Clapping on
Thank
behalf
you.
of everybody.
And it's really great to see the level of interest. So thank you so much. I really enjoyed getting your questions and discussing.
And also wanted to thank you, Dr. Miao, for connecting us for this seminar. And it's my pleasure to meet you today. We look forward to maybe host you someday on the campus.
Thank you.
Not too far from now, hopefully. Okay.
Thank you.
Okay, then, everyone, goodbye. Thanks for joining us today.
Okay, thank you. Bye-bye.
Okay, bye-bye.
Bye.